This is the narration for the Unit 9 PowerPoint. We're going to be talking about states of matter. So solids, liquids, gases, and the changes that happen between those states. All right, so I'm sure this is something you already know about. What are the three states of matter? Solid, liquid, and gas. We're going to define them a little bit more carefully. All three states have certain properties that can help distinguish between the states, and so we're going to look at each of those in turn and see what's different between the different states. This little video is a good one to watch. It kind of shows you something going from a solid to a liquid to a gas, and it may help you visualize it. Density, so that's the first thing. You may remember back from the beginning of the semester that density is just defined as the mass per unit volume. So how much, it's kind of a measure of how much empty space there is. So if there's a lot of mass in a small amount of volume, that's something that's very dense. If there's a small amount of mass in a large amount of volume, then that's something that's not very dense. So solids tend to be compounds where particles are close together and held in fixed positions. And so because of that, there's very little empty space between particles. They're packed really close together. We can consider them dense. And you can see in the picture down at the bottom, the solid is closely packed, and so solids have high density. The liquid state, the particles are still close together, but they're not held in fixed positions. They move around a little bit more, and there's a little bit more empty space between them. And so liquids in general are usually a little less dense than solids. There is one exception to that rule, and it happens to be water. Maybe we'll talk about that later in this slideshow. Water liquid is actually slightly more dense than the solid. Anyway, the gaseous state is where particles are far apart and there's a lot of empty space between the particles, and so gases have low densities. Okay, the shape is another way that you can think about solids, liquids, and gases. Solids, as we said, their particles are held together in fixed positions, so they have their own definite shape, and you don't need a container to hold them. They have their own shape. Liquids, of course, are held together but not in fixed positions, and so they will take the shape of the container, but only to the extent that it is filled. So you can see in the middle picture, the volume in these two containers are the same, but it takes the shape of the container, and so they might look a little bit different. Gases, because the particles are not held together, have indefinite shape. They take the shape of and totally fill the container it's in. So you can see in the far right picture, if the gas is contained in half of that smaller box, and then if we take that middle section out and open it, the gas will expand to fill the whole container. Okay, compressibility. Compressibility, as the name implies, how much can you squeeze it or put pressure on it and make it compress it down. And so it's the change in volume of a sample that results from a change in pressure. So if you press something, how much will it compress? Solids, as you can imagine, have very low compressibility. There's very little empty space, and so you can't squish the molecules much closer than they already are. Liquids also have a low compressibility, but a little bit better than the solid. So you can usually compress a liquid down a little bit more. But if you've ever tried to fill a bottle with water and then try to put the cap on it, you know that you can't squish it very much. So liquids still have low compressibility. Gases have a large compressibility because there's a lot of empty space between the molecules, so you can push them close together. And as you I'm sure know, it's very easy to take a gas and compress it down into some kind of container. Okay, and then finally thermal expansion. Thermal expansion is how much does something change in volume, how much does it expand if you heat it up. So solids have very small thermal expansion, liquids have small thermal expansion, and gases have moderate thermal expansion. So again, as you can imagine, liquids won't expand a whole lot, but a little bit more than solids, and gases can expand more than that. So this chart gives you just a little bit of a summary of the physical properties of solid, liquids, and gases. So solids have high density, a definite shape, small compressibility, and very small thermal expansion. Liquids have high density, but a little bit lower than the solids in general. A big exception to that would be water. Water has a higher density, liquid water, than solid water. But in general, it's lower. Liquids have an indefinite shape that take the shape of the container, but only to the extent it's filled. Liquids have small compressibility and small thermal expansion. And then gases have low density, indefinite shape that takes the shape and fills the container, has large compressibility and moderate thermal expansion. Okay, so what we're going to do now is talk about how solids and liquids and gases change into one another, and we're going to do that by talking about the kinetic molecular theory of matter. So when we look at things every day, what we're doing is we're looking at the macroscopic properties. So liquids are wet and they flow. We can see things that happen on the macroscopic level, but of course this is all being all happening at a molecular level that we can't see. We don't know exactly what's happening. So the kinetic molecular theory is a way of picturing what the molecules and atoms are actually doing to cause the properties that we can observe at the macroscopic level. So the kinetic molecular theory has 5 postulates, or let's say things that we're going to assume are true. So first of all, we're going to assume that matter is made up of tiny particles called molecules. We don't know that for sure, but there's pretty good evidence saying that there is. For this theory, we're going to assume that. We're going to assume that particles are always in constant motion, and so for that reason they possess what we call kinetic energy. We'll look at that in just another second. Particles also possess potential energy as a result of repelling or attracting each other. Now, the particles will speed up if the temperature increases. They will slow down if the temperature decreases. And then finally, particles will transfer energy from one to another during collisions. They run around and they collide into each other. But when they collide, we're not going to lose any energy in the collision. It's not necessarily true, but we're going to assume that for this theory. Okay, so first let's talk about kinetic energy versus potential energy. So you probably have heard in the past, kinetic energy is the energy of motion. And so in what we're talking about in molecules, it just means that the molecules are moving around. We can also, since kinetic energy is related to both mass and velocity or speed, we know a couple of things. A larger particle will have more kinetic energy than a smaller particle if they're moving at the same speed. You can sort of think of a truck and a Mini Cooper both moving down the street at 30 miles per hour, and if the truck collided with a wall, it would be a lot worse than if the Mini Cooper did. But we can also, kinetic energy also depends on the velocity, and so if we have the same size particle and one's moving faster than the other, then it will have more kinetic energy. So again, think about 2 Mini Coopers. If one was going at 30 miles per hour and the other was going at 90 miles per hour and they collided into a wall, of course the 90 mile per hour one would be going fast, have more energy, more of a collision. So kinetic energy is the energy of motion, depends on both the size and the velocity of the particle. And potential energy is stored energy, and on the molecular level, what we consider potential energy is partly in bonds, but also the energy that a particle has because they're attracted to each other or repel from each other. So that's what we're going to look at in this chapter. All right, so we talked briefly in another unit about forces between particles, and we're calling these cohesive forces. Well, there's 2 kinds. There's cohesive forces and disruptive forces. So first, let's look at the cohesive forces. Those are the ones that we have already talked about back in Unit 5 and 6. So polar forces, or dipole forces, are forces that hold molecules that are polar together. So a positive end of a polar molecule is attracted to a negative end of another polar molecule. And then we had hydrogen bonding, which are very strong polar forces that have to do specifically with a hydrogen attracted to an O, N, or F. And also the hydrogen has to be attached to an O, N, or F, and then is attracted to another O, N, or F. And we know that those are really strong polar forces. Then we have the dispersion forces, which are attractions between nonpolar molecules. Since a nonpolar molecule doesn't have any charges, but we sometimes would call them an induced charge because they might have a charge for a temporary instant and then cause a charge separation in another molecule, but it happens very fast, and so they're very weak interactions. And then finally, ionic forces are forces between ions, which are fully charged particles. We looked back at Unit 5 and 6. Hydrogen bonding, out of the top three, hydrogen bonding is the strongest, and then polar forces and dispersion forces. Generally, ionic forces are even stronger than hydrogen bonding. We also have disruptive forces, and that has to do with particles that are moving. So if two particles are moving very fast by each other, there's less likelihood that they'll be attracted to each other. Whereas if two molecules are moving very slowly by each other, then the cohesive forces may take over and the disruptive forces. So, but a disruptive force is something that keeps the particles apart, and that generally has to do with molecules moving around. Okay, so the balance, as I started to talk about, the balance has to do with whether cohesive forces or disruptive forces take charge, are the dominant force. So at high temperatures, in general, we know that particles are moving very fast because as we increase temperature, the particles start moving faster. So at high temperatures, usually the disruptive forces take over because they're moving so fast by each other, the attractive forces don't have a chance to come into play. So usually that's when there's weak forces holding the particles together, whereas there's high disruptive forces because they're moving fast. And so overall, disorder prevails, disruptive forces prevail, and that you're generally talking about the gaseous state. So if you decrease the temperature a little bit, what happens? The molecules start to slow down. As they slow down, those cohesive interactions start to take over. So as the molecules move slower, they can't pull apart from each other as much. So they're held loosely together. There's some moderate forces holding the particles together. Moderate movement, not enough to pull them apart. And so generally we think of this as the liquid state. And then finally, if you decrease the temperature even more and the molecules slow down, then the cohesive forces become very important. They're very hard to pull apart because the molecules aren't moving fast enough to pull them apart. And so this is considered the solid state. Molecules are held closer together. There's little movement, but the interactions are strong. Now here's the thing, if you're talking about a particular molecule, like let's say you're just talking about water, the forces between the two molecules never change. It just has to do with whether the disruptive forces are greater or less than the cohesive forces. So the hydrogen bonding between water molecules will always be the same, but if molecules are moving fast, there's less likelihood that they're going to be held together, whereas if molecules are moving slow, there's very little energy to pull them apart. And so that's really the difference between the three states. All right, here's just a nice little picture. The solid state, particles are close together, held in fixed positions. Liquid state, they're still close together, but they take the shape of the container. And then finally, gaseous states are far apart, where the disruptive forces take over in the gaseous phase. All right, this little chart tells us the names as we change states. You probably already know at least most of these. Well, if the change is caused by adding heat, if you add heat to it, we call that an endothermic change. If a change is caused by removing heat, we call that an exothermic change. So let's look at the endothermic changes first. So if we have a solid and we put heat in to get a liquid, then that's called melting, as you probably already know. If you take a liquid and you put heat in and change it to a gas, that's called evaporation or vaporization. If you happen to have a solid and you're able to put enough heat in that it directly changes to a gas, we call that sublimation. Now, not all molecules will do that, but one example, carbon dioxide, if you have dry ice does not go through a liquid phase, it goes straight from a solid to a gas phase, so that's called sublimation. Now, the other, if you're cooling things down, in other words, you're taking heat out, exothermic, if you start with a gas and you cool it down to a liquid, we call that condensation. If you take the liquid and cool that down to a solid, we call that freezing. Sometimes it's called crystallization. And if we take a gas and we cool it down directly to a solid, then that's called deposition. All right, and this just sort of summarizes what I just said. So again, remember that endothermic, sometimes it gets a little confusing, but endothermic means you have to put heat in. So you're putting heat in, you're moving molecules faster, and so attractions become less important, and the disruptive portions become more important. And then exothermic process is where heat's coming out, and so things are cooling down because the heat is being removed, and so molecules move slower and get closer together. All right, these are just, if you have some time, you might try out these websites that, again, they just sort of show the difference between solids, liquids, gases, changing phases. They're all just different ones that I found. But you can do that on your own because it doesn't work on this YouTube video. All right, and before we finish, we're going to talk just a little bit about a heating and cooling curve. This is like a graph that we're going to show how temperatures change as we add heat. That's called a heating curve, and a cooling curve then is a graph that shows how temperature changes as we remove heat or cool it down. So in both of these curves, we're going to have temperature on the y-axis and heat added or removed on the x-axis. So you can read this. You can see that during a phase change, the curve shows a flat line or plateau. This is because when something is being heated, what you have to do to go from solid to liquid, you have to put energy in, and instead of the molecules getting faster and getting hotter, all the energy during the phase change goes into breaking attractions. And then at a cooling curve, as the heat is released, it comes from particles forming attractions rather than slowing down. So I'll go through that on the next slide in just a minute. I'll kind of go through the whole. So here's what a heating curve looks like. So you can see on the x-axis we have energy added, and on the y-axis we have temperature. So if we have a solid and it is below its melting point, it's only a solid, and if we add heat to it, what's going to happen, it's not going to melt quite yet. It can't melt until it gets to its melting point. So what's going to happen is that solid will start to heat up. So as we add energy, the solid raises its temperature, it heats up. So on this graph, from point A to B, we have a solid that is heating up, and that's why the slope is kind of going up. Temperature's going up as we add energy. Now when we get to point B, that's the melting point. When we hit B, now the molecules are moving fast enough that they are starting to pull apart from each other, so which is melting. So from the point B until the point C, what we have present is both solid and liquid, because as we add energy, rather than making the molecules move faster, what the energy is doing is it's pulling apart those attractions, and so the molecules are moving farther apart. So they're not really moving faster, which is why the temperature doesn't go up during this part. they're pulling apart from each other. So from B to C, the temperature stays constant throughout the whole time that the solid is melting. So from B to C, you have both solid and liquid present. Now at point C, that's the point where all the solid has finished melting, and so we only have liquid present. So what happens if we keep adding energy? At this point, they're farther apart from each other. All the attractions are pulled apart from the solid, and so if we add more energy, the molecules will just start moving faster again. And so as they move faster, they are going to heat up. So faster molecules means more kinetic energy, which means higher temperature. So from point C to D, only liquid is present, and during that time, the molecules will start moving faster and faster, which means the liquid will be getting hotter and hotter. Finally, when it reaches point D, which is the boiling point, all the liquid, now the liquid is going to start, the attractions are going to start pulling farther and farther apart. So from point D to point E, all the energy that we're adding is going to go into pulling the molecules apart, and so that's going from a liquid to a gas. So again, from points D to E, we're going to have both liquid and gas present. Evaporation is going to be taking place, and it will stay the same temperature, it will stay the boiling point until every drop of the liquid has evaporated. Then finally, if you've got everything now in the gaseous phase and you keep adding energy, all that's going to happen is the gas is going to get hotter, the molecules will continue to move faster and faster. So that's what a heating curve is. So a cooling curve is really just the same thing but in the opposite direction. So if you start with a gas and you start to remove heat, you start to cool it down, at first what's going to happen is the gas molecules will start moving slower and slower, but they'll still remain a gas. Then at some point at the boiling point, but in reverse, it'll start to condense. At that temperature, now the molecules will start the attractions start to hold them together closer, and so now you've got some of the gas condensing to a liquid. So from the point where it's flat, you have both gas and liquid around. Finally, once all of the gas has become liquid, we can cool it down, slow the molecules down, and so the temperature of the liquid will continue to fall until we get to the freezing point. At the freezing point, if you keep removing heat, the molecules will get closer together, and so all during that flat part again, that's on the line of 0, that's where the liquid and the solid are both present, and during that time, all of the liquid is freezing. When you finally get to the end of that flat part, it's all turned to solid, and then if you continue to remove heat, eventually the solid will just get colder and colder. So the cooling curve is just backwards from a heating curve. So I'm going to go through the same thing just real quickly, but just talking about ice in particular. So we're going to imagine a cube of ice starting at negative 20 degrees, and what we're going to do is we're going to add heat at a constant rate until all of the ice is converted to steam at 120 degrees. I'm going to talk about it as I have the next slide up. So again, energy added is on the x-axis and temperature is on the y-axis. So if we have the ice, again, at negative 20 degrees, since that's not at its melting point, if we add heat, and let me keep in mind that we're considering a perfect heating. So of course, if you actually take an ice cube and do this, it's not going to perfectly work like this because the outside will heat faster than the inside. So what we're assuming is a perfect world where everything heats evenly all the way around. So it may be a little bit hard to imagine from everyday experiences. But anyway, if we have an ice cube that's at negative 20, before it can melt, it has to heat up to 0 degrees. And so that as we can add enough energy to the ice to bring it up to 0 degrees. Now at 0 degrees, that's where, of course, the attractions and the ice cube melting are just holding together. And so if we add any more energy, the attractions will start to break apart. So there's still some attractions, but now they're just able to move farther and farther away from each other. So the molecules aren't moving faster, but they're moving farther away, and so the ice begins to melt. So again, from point B to point C, we have both ice and liquid water present, and the ice is melting. So again, if we continue to add heat at point C, all the liquid will have melted. All the ice will have melted. It's all liquid. And then if we keep heat to it, the liquid water will heat up, heat up, heat up. But then when it gets to 100 degrees Celsius, of course we know that's the boiling point of water, it will start to evaporate. At that point, the molecules are getting so fast that the attractions are even farther apart, and now you're able to break them. So as you add the energy, those interactions are breaking, and so throughout from D to E, we have both water and steam. The evaporation is taking place, and then finally at E, all of the water has vaporized, and then from E to F, you have steam only in the gas phase, and it continues to heat up past 100 degrees. So past 100 degrees, you can't have any liquid. It's got to be all gas. And from 0 to 100, you only have liquid. And if you're changing phases, they stay at the melting point or the boiling point.